There are some problems in math that just feel, well, eternal. Puzzles that have been around for centuries, almost daring someone to find a solution. Today, we're going to look at one of those puzzles and a pretty revolutionary new theorem that says it's finally cracked the code.
Okay, let's just dive right in. What you're looking at is a 20th degree polynomial equation. It's a mathematical beast for sure. So what we're trying to do here is find the exact values for x that make this whole thing true. And when I say exact, I mean perfect. No rounding, no close enough. We want the perfect answer.
And that, right there, is the big question, isn't it? The one that stumped mathematicians for ages. When you get to equations this complex, is a perfect, precise answer even on the table? Or are we just stuck with making really, really good guesses forever?
So, to really appreciate the solution, we've got to first understand the sheer scale of the challenge we're actually up against.
Yeah, this is not a new problem by any stretch of the imagination. For hundreds of years, finding the exact solutions, the roots for polynomials this big, has been one of those great big hurdles in algebra. It's a wall that some of the brightest minds in history have run straight into. So why is this thing so darn hard to solve? Well, the answer really lies in the tools that we've been trying to use. Let's take a look at the two traditional ways of doing this. Okay, so this slide really lays out the big dilemma. On one hand, you've got classical algebra, which is all about finding those perfect, exact roots. But here's the catch. A famous theorem, Abel's theorem, basically proved that for most equations this complicated, there's just no simple formula. It's a dead end. So on the other hand, you have numerical methods. These can get you close to an answer, but at the end of the day, they're basically a super sophisticated form of guessing. And they're always plagued by these tiny little rounding errors that mean you never get a truly perfect solution. I love this way of thinking about it. It's like classical algebra has a big ring of keys, but none of them actually fit these really complex locks. And numerical methods, they don't even bother with a key. They just try to guess the combination, getting closer and closer, but never quite hitting that final number. Neither one can just elegantly open the door. But what if there was a new key? What if someone came up with a totally different way of thinking about the problem, one that just bypasses all those old limitations? Well, this is where our story takes a really interesting turn. And that's where we get to Azawidi's theorem. This is the breakthrough we've been talking about. It's a method designed specifically to do what the other two couldn't: deliver precise, symbolic, and most importantly, solvable roots for these polynomials that everyone thought were unsolvable. And this right here is the heart of it. We're not talking about getting pretty close anymore. The whole idea is to completely ditch approximation and step into the world of absolute mathematical certainty. We're moving from guesswork to a guaranteed exact answer. All right, so how on earth does it actually work? Let's pop the hood for a minute and see the elegant step-by-step process that makes this whole thing possible. Okay, so the secret sauce here is a technique called recursion. It's a really clever idea. Instead of trying to wrestle with this whole massive equation at once, the theorem breaks it down. It calculates a series of what are called symbolic coefficients. You can just think of them as perfect mathematical building blocks for the final answer. And here's the cool part. Each new block is calculated using the one that came right before it, creating this perfect, unbreakable chain of logic. So here's the game plan, step by step. First, you pull out your starting ingredients right from the original equation. Then you use this special recursive formula, think of it as a recipe, to create the next piece from the one you just made. And you just keep doing that. For our equation, you do this 20 times. Once you have all 20 of those exact symbolic coefficients, you've got everything you need to build the perfect solutions. It's systematic, it's methodical, and it's precise. So the process kicks off calculating that first symbolic coefficient from the initial values. Then, using that brand new result, it moves on to calculate the next one. And the next. Each step building perfectly on the last one. This chain reaction just keeps chugging along, systematically working its way through all 20 degrees of the polynomial, all the way to the very end. And what we're left with is a complete set of these precise values, with absolutely zero approximation at any point in the process. So what's the big payoff? After all that recursive work, what does the perfect, exact solution to a 20th degree polynomial even look like? And there it is. Now I know that looks pretty intimidating, but let's just talk about what's actually happening here. Those S values, those are the super precise symbolic coefficients, the building blocks we just spent all that time calculating. And that E with the I and the exponent, that's just a powerful way of describing rotation in math.
So by combining these exact building blocks with a very precise kind of rotation, this one formula can pinpoint every single one of the 20 solutions. It's the mathematical key that finally fits the lock perfectly. And the key thing to get here is that writing the answer this way isn't some random choice. This is the natural language of the solution that just pops out of that recursive process. It's the elegant combination that unlocks the entire problem. Okay, that's really cool and all, but what does a breakthrough like this actually mean? For math and maybe even beyond. Why should we care? Well, it really matters. I mean, this is a huge shift, right? We're going from close enough to dead on. It gives us a way to get around a historical roadblock that stood for centuries. It gives us a reliable, structured path to a perfect answer. And think about it. For fields like physics, engineering, or cryptography, where being just a tiny bit off can be a total disaster, having a tool that gives you a perfect answer, that's a real game changer. And that kind of leaves you with this fascinating thought, doesn't it? If a problem that was considered unsolvable for centuries can now be cracked with a new, systematic approach, it really makes you wonder, what other big, hairy, unsolvable problems are out there just waiting for someone to find the right key?